In this next lesson on moments, we're going to focus on ladders and bridges problems. And this actually comes under chapter 7 because it involves quite a lot of resolving forces as well. Now this is a question that we've already looked at earlier on in this series of lessons. So we've got a uniform rod PQ, you can see here, and it's hinged at point P. So it's rotating around here. And it's held in equilibrium at an angle of 50 degrees to the horizontal by a force of F, which is perpendicular to the rod. It's got a length of 3 meters and a mass of 8 kilograms. Find F. So what we did was we resolved this 8G. If I make this a bit longer, we can resolve it into perpendicular and parallel, just like we would do for things on a slope. So if that's 50, this is then 8G cos 50, and this is 8G sine 50. Now in terms of moments, I can take moments about P, to this point at the bottom, and remember it is the perpendicular component of the force. So in this case it's going to be the 8G cos 50, because this is perpendicular to the distance. So that's 8G cos 50 times the length, so from here to here, that's half the length of this rod, because it's uniform, so that's going to be times 1.5. Okay, and that is causing it to try and spin clockwise. Now, because it's in equilibrium, that's equal and opposite to this force, which is trying to make it spin anti-clockwise. And that force is already perpendicular. So we can just use F times the distance away, which is 3 meters away. And then I can solve this equation to find F. So 8 times 9.8 times cos 50 times 1.5 divided by 3. So you get 25.2 newtons. Okay, so we're going to do similar problems to this. Okay, for this next example, we've got a slightly different context. So we have got a plank or a rod, which it says is uniform, and it's resting on a peg, okay, a smooth peg. So it says this uniform rod AB, so this is point A, this is point B, of mass 40 kilograms, and it's uniform, so we can put that on. So let's put the weight on halfway. This is 40G. With end A, and length 10 meters. Let's just jot that down. Let's put our length here on as well. So this is going to be 5 meters. The rod rests against a smooth peg C, where A to C is 8 meters. Let's put that on as well. The rod is in limiting equilibrium at an angle of 15 degrees to the horizontal. Okay, so you can put that on there. Now, things that are different here, obviously we've got a peg rather than a wall or anything like that, so that's slightly different. But we've also got rough horizontal ground, it says. So there's going to be some frictional forces on the ground down here as well. Now, we will still have a reaction force from the ground upwards, so that's going to be RA. Now the frictional force, deciding is it going to go left or right, the way that I think about friction here is imagine what would happen if there wasn't any friction. So imagine that this floor here was incredibly slippery. If you just balanced it on a peg, it would probably kind of slide out this way, wouldn't it? If this floor was super duper polished, the bottom would slide along the floor that way. So that means that friction must be acting this way. So I'm going to call this, I'll just call it friction, FR. Okay. Now, other forces involved, there's going to be a reaction force at C. And because this is just a surface, which is smooth, it's a smooth peg, the reaction force is going to be perpendicular. Okay, I'm just going to call this RC. So this is perpendicular to the rod. Okay, because you can think of it as almost like a tangent to this circle. It's perfectly flat and it makes it at 90 degrees. Because it's smooth, it's like a perfect kind of contact point, so it just acts perpendicular. Okay, other things we could do, we could resolve the weight here, just like on the last one, because we're probably going to need to use the perpendicular component of it. So just do exactly the same as we do for slopes. So this is 15, so this is 40G cos 15, and this is 40G sine 15. Okay. And now we can see if we can work out the things that it's asking us to work out. So for part A, we'll do it underneath here. The magnitude of the reaction at C. Well, let's just take moments about here. Okay. So if I do moments about A, that means I don't have to worry about RA and FR because they're both distant 0 away. Things I do have to worry about is this component here. So I've got 40g cos 15, it's a perpendicular force, times the distance of 5. That's trying to make it spin clockwise. Keeping it in equilibrium is this force here, and it's already perpendicular, so that's just RC times the distance of 8, and that's trying to make it spin anti-clockwise. And I can solve this equation to find RC, and I get 236.7 newtons. Okay, so that's that bit. Now part B, find the coefficient of friction between the rod and the ground. So we want the coefficient of friction down here. Now coefficient of friction, the equation that we remember is F equals mu R. But we're trying to find mu, so I suppose we could write mu equals F over R. So if I can work out what the friction is, and I can work out what the reaction force is, then I can work out what mu is. So that's what we're going to do here. And the way we're going to do it is we're going to resolve vertically and horizontally. So if I resolve all of my vertical forces, so I'm not doing moments, I'm just looking at forces here. If I just look at the vertical forces, I've got RA plus, now I want to split this RC up into a vertical component and a horizontal component. Okay. In terms of the angles, if this is 15 here, that angle in there is 15. So this angle here, remember this is a right angle, must be 75. Let's just zoom in and write that in. Okay, so that's 75 in there. Sorry, that's a bit small on my diagram. But the vertical component is going to be RC sine 75. So those are my vertical bits, and that must equal the 40g downwards. Okay. Now I already know what RC is, so I can just substitute that into here, and I can solve that to get RA. So RA is 163.4 newtons. So I've got one component of this equation. Now what I'm going to do is do the same thing but horizontally. So forces to the right. So I've got FR. Now 40g, that's purely vertical, so it doesn't even have a horizontal component, so I don't need to worry about this. But I do need to worry about this horizontal component here, which is going to be RC cos 75. Okay, and this one's to the right, this one's to the left, so they must be the same. And I know what RC is, so I can work out FR, and it's 61.3 newtons. And then finally, I can use my equation mu equals F over R. So I get 61.3 over 163.4. So mu is 0.38. There we are. So you can see at this sort of question, it combines all the things that we've done in mechanics so far, really, moments and resolving forces at angles. Okay, here's one for you to have a go at. Pause the video, have a go on yourself, and then I will go through it in a minute. So this is similar to the two last examples we've done. We've got the measurements on the diagram here already. So we've got to find the tension in this string, so we're trying to find this value of T here. Okay. So we can put the weight of the rod on as well. So I would have probably drawn this diagram at a bit of a bigger angle just to make it easier to fit in, but here's the weight, and it is 4 kilograms, so that's 4g. Resolve that, so that's 20 up there, so this is 4g cos 20. It's this component here, the perpendicular one. So if I take moments about A, then I will have 4g cos 20 is the perpendicular component, times a distance of 0.7, because it's uniform and it's halfway up the rod. That equals T, which is already perpendicular, times the length 1.4. So you can solve that to get T equals 18.4 newtons. Now part B, Given that the rod is about to slip, find the coefficient of friction between the rod and the ground. So, same idea as before, we need to think about the reaction force at A, and we need to think about the friction. The friction again was going to go to the right, just because if there wasn't any friction, if it was really slippery, the bottom of this plank would just slide along that way. So what we need to do then is resolve vertically. So I've got RA is vertical, plus, now there's going to be a component of this T here. If I draw them on, so there's the vertical bit, there's the horizontal bit. This angle in here is going to be 20. So this angle here must be 70. So this vertical component is going to be T sine 70. So those are my two vertical upwards forces. They must be equal to the 4G. And I know what T is from before, so I can substitute that in. So RA is going to be 22 newtons. Now I need to find the frictional force. So horizontally, I've just got FR equals the horizontal component, which is going to be T cos 70. And we know what T was before, so we can find FR is about 6.3 newtons. And then we can just use F equals mu R. The reason that we can use equals is to do with the fact that it's on the point of slipping, or it's about to slip, so that we know that friction must be at a maximum, so we can use this equation. So we've got mu equals F over R, or 6.3 over 22, which gives me about 0.29 as my coefficient of friction here. Okay, so not too tricky. It does kind of involve lots of different skills we've done before. Drawing a diagram and marking on your angles is obviously really important. Okay, in this next example, I want to think about hinges in particular. So here we've got a uniform rod. I'm just going to take this picture and make it a bit bigger actually. Just so I can draw on it more easily. Okay. We've got a uniform rod of mass 5 kilograms. Let's put the weight on. Okay, so there's the 5G. We might as well resolve it whilst we're here. So it's going to be 5G cos 25, because this is 25 up here. And this would be 5G sine 25. Okay. And length 4, so obviously this is halfway, so this is going to be 2 meters away. Has its end A smoothly hinged, so what that means is it's just allowed to rotate around that point there. The rod is held in equilibrium at an angle of 25 by force F. So before we always had it perpendicular, but now we've got force F at an angle, which makes it slightly more complicated, but we know how to resolve forces. So the first thing to do is find force F. So let's take moments about A, so around this pivot, this hinge here. So moments about A, I'm going to have 5G cos 25, the perpendicular bit of the force, times the distance. Well, it'll be halfway, so that's times 2. And that equals, now it needs to be the perpendicular component of the force, which I could draw on here. Okay, I could also draw it here if that makes it clearer, because it's technically acting at point B. Okay, so that's going to be F sine 40, is that component there, times the distance, which is 4 meters away. I can then solve this to find F, and I get 34.5 newtons. Okay. Now the second bit, find the magnitude and direction of the vertical component of the force acting on the rod at A. What I'm going to change this to is, I'm going to take out this bit here. So it's going to say, find the magnitude and direction of the force acting on the rod at A. So there's going to be some forces on the hinge here. Okay. I don't really know where those are. So what I'm going to do is I'm just going to label, there is some vertical forces, I'm just going to call it Y, and there is some horizontal forces, I'm going to call it X. Okay, just because there's going to be a vertical component and a horizontal component. I don't really know much else than that though. Okay, and now what we're going to do is we're going to resolve vertically and horizontally. So vertically, I can say that Y plus, now I want the vertical component of this, so I'm just going to rub out these lines here, just so I can doodle on it a bit easier. I want the vertical component, so what I'm going to do is I'm going to split it like that. Okay. Now this big angle here is 40. Remember, this line here is horizontal, so I get a Z angle. So this is 25 in here, which means that this bit, the whole thing was 40, that's 25, so this little bit must be 15. Okay, so a little bit of kind of geometry in there. So that means this vertical component is F sine 15. Okay, so there's my two vertical components, and they must be equal to the 5G. Okay, I know what F is from before, so I can solve this to find that Y is about 40 newtons. Now I'm going to do the same horizontally. So I've got force X here. That must be equal and opposite to this component, which would be F cos 15. So that means that X is 33.3 newtons. Okay. So I've got my two components, so now I can find out what actually is the force on this point. So basically at point A, what I've got is I've got this hinge, I've got a vertical force of 40, I've got a horizontal force of 33.3. Okay. You could even write it as a vector if you wanted, and we've done this sort of thing lots of times. So we've got horizontal 33.3, vertical 40, so the magnitude I can work out using Pythagoras. So the magnitude of the force on the hinge is going to be 33.3 squared plus 40 squared, square rooted, which is 52 newtons. As for the angle, we've done this sort of process lots of times too. The angle would be inverse tan of 40 over 33.3, which is about 50 degrees. So we could say 50 degrees above I, is probably the easiest way to say it. Okay. In terms of where that would be on my diagram, that means that there's overall a force maybe a bit like that on the hinge to keep this all in equilibrium. Okay. So if it asks you about forces on the hinge, this is a good way of doing it. So just label it as Y and X, and then do the same process as we did in the last few questions, just resolve horizontally and vertically. And you might need to think a bit carefully about this sort of thing. Okay. So moving on to ladders, this is another really common context, and we did this question a couple of lessons ago. So we've got a uniform ladder of mass 5 kilograms and length 2 meters. So let's just draw its weight on. So we've got, this is 5G, we can resolve it like that, and it says the angle is going to be 50 degrees. Okay, we want to find the reaction force at the wall. Just like that question earlier with the peg, the reaction force here is going to be perpendicular. I'm going to call this RW for the reaction force at the wall. All we're going to do is just take moments about, let's call it point A. So I've got 5G cos 50 times the length of 1, because it's halfway up this ladder, of length 2 meters. And that equals, and it's got to be the perpendicular component, so that bit there. This angle here must be 50 as well, because of alternate angles or Z angles. So that's RW sine 50 times the length away, which is 2. And I can solve this to find R. Let's just do that now. So I get about 20.6 newtons. Okay, so we're going to extend some ideas related to this question now. Hopefully this example seems fairly straightforward after some of the other ones we've done in this lesson. So in this question, we've got the same sort of thing as a ladder question, but we've got some friction involved too. And there's lots of information here. Most of it's on the diagram though. So we've got a ladder of length 5, you can see that in the picture, a mass 18, so let's just put the weight on already. Might as well do that straight away. So that's going to be halfway, so we can put the weight on here. So that's 18g, and it says it's inclined at angle alpha. So here's alpha here. This is also going to be alpha. So this is 18g cos alpha. And then we're told tan alpha is 4/3, and we've dealt with this sort of thing before. So tan alpha is 4/3, so we can draw a little triangle like this. Opposite over adjacent, so this is 5. So sine alpha is going to be opposite over hypotenuse, so that's 4/5. And cos alpha is adjacent over hypotenuse, which is 3/5. Just so we've got those there for later. Now it says there's friction on the floor. The coefficient of friction is mu. A woman of mass 60 stands on the ladder at point C, which is 3 meters from the bottom. So we need to draw another weight arrow on here. Just going to draw that down here. I'll just draw it smaller. It's not to scale or anything like that. It's whatever I can fit in. And her mass is 60g. This is still alpha. So this is 60g cos alpha. So we've got two masses we have to take into account here. The ladder is uniform and the woman is a particle. Okay. And we've got to find mu. So to find mu, we're going to do the same strategy as we did before. We're going to need to find out the reaction force here. So I'm going to call that RA. And we're going to need to find the frictional force here. So I'm going to call that the friction at A. Okay. And then we can use F equals mu R to help us find mu. Other forces that are going to be important, there's going to be a normal reaction force at the wall, and it is perpendicular to the wall. So I'm going to call this the reaction force at B, or the wall. I'll do W for wall. Okay. Lovely. There we go. And because it's a smooth wall, that's why we've just got a reaction force. We could have a situation later where there's friction here as well. Okay. And then we can have some friction acting up and down the wall as well. So let's start to analyze this problem then. Let's stick with the easy stuff first. Let's just resolve vertically first of all. So vertically we've got RA upwards, and that must be the same as 18g plus 60g. There's no other vertical forces. So actually RA is 764.4 newtons. We can work that out straight away. So we've kind of got half of this already. Now we just need to find what FA is. So let's resolve horizontally. FA, the friction at A, that must be the same as this force here, as RW. And those are the only horizontal forces I've got. These two weights are only vertical, they've got no horizontal component. So this isn't very useful so far. All we know is that the friction at A is the same as the reaction of the wall. That's what that tells us. So we need to work out RW, and then we know what FA is. So now we can do moments about A. We'll just do moments about the bottom of the ladder here. So we have got 18g cos alpha, so that's the perpendicular component, times the distance away. It's halfway up the uniform ladder, so that's going to be times 2.5 meters. We've also got 60g cos alpha times 3 meters up the ladder. That was the woman who was on the ladder. I'm just going to move this to the side because it's getting a bit long. That must be equal and opposite to the moment caused by this force. Remember, we want the perpendicular component here. This must be alpha as well because it's an alternate angle. So it's going to be RW sine alpha times a distance of 5 meters away. Okay. Now we know what cos alpha is. We know what sine alpha is. 4/5 and 3/5 up here. So we can stick those values in. And if we do that, then we can solve it to find that RW is 330.75, which obviously means that FA must be 330.75. So now we've got our friction and we've got our reaction force at A, so we can find what mu is. So we've got 330.75 over 764.4, So mu, the coefficient of friction, is about 0.43. There we are. So it's just about putting together all the things that we already know how to do, but also being accurate when we do those. Okay. Here's one for you to have a go at. Same sort of idea. We've got a smooth wall and we've got rough ground. So have a go at this one yourself and then I will go through it. Okay. So we've got a uniform ladder of mass 10. So I'm just going to put its weight on here. And it says it's at angle 65. So this is 65 too. So we've got 10g cos 65. The length of the ladder is 5 meters. So this is obviously 2.5 meters up. Here's a smooth wall, so we've just got a reaction force here. I'm just going to call it RW. I think in the question they call it S, but that's fine. Okay, other forces involved. It says it's rough ground, so we've got a reaction force here. Let's just call it A again. And we've got a frictional force, so the friction at A. Okay. So to find the magnitude of this reaction force, we're going to take moments about A, about the bottom of the ladder. So I've got 10g cos 65 times halfway, so that's 2.5. That equals, we want the perpendicular component, this angle in here is going to be 65. So that's RW sine 65 times the length 5 meters away. And if we solve that, we get RW, or in this case S they've asked for, is 22.85 newtons. So that's part A. Part B, the normal reaction force at the ground and the frictional force at the ground, so that's RA and FA. So if I resolve vertically, then I've simply got RA must equal 10g. There's no other vertical forces, so that's obviously 98 newtons. If I resolve horizontally, the frictional force, that must be the same as RW, which is 22.85 newtons that we just worked out. Part C, the least possible value of the coefficient of friction. So this is assuming that we are maximum friction, it's on the point of sliding perhaps. So we can use F equals mu R. So then mu is F over R, well that's 22.85 over 98, which is about 0.233. State how you've used the assumption that the ladder is uniform in your calculations. So if it's uniform, we can assume that the center of mass is halfway up the ladder. Okay, that's what we can assume there. Now, things that can make these questions slightly more complicated, they could give you friction at the floor and they could give you friction up here. If they were to do that, let's just take this diagram and draw on it underneath. So if there was friction at the wall as well, then as well as a reaction force here, there would also be some friction here. So again, imagine what would happen if the wall was smooth. So if it was totally smooth and it was really polished, it would basically slide down the wall, wouldn't it? The wall would be too slippery and it would just slide down. So there must be some friction stopping it moving down, so going upwards. So we could have some friction at the wall as well. And these could then be two different values of mu, just to make it especially hard. Okay, and very occasionally you get exam questions like that. Okay, but you still do the same process. You still resolve up and down, and left and right, and take moments about a point, and you'll be able to get to the answer. And that's about as hard as they would get, to be honest, something like that. So questions to do now, you can have a look at exercise 7D, questions 1 to 8. So this is in chapter 7, not in the moments chapter, which is all about ladders and planks on pegs and things like that. And also hinges are in there too. And then next lesson we will do some time on exam questions on this topic as well, because it is quite a tricky topic, but it's also quite a good topic in the sense that it practices lots of different mechanics skills at once. So I'd advise you have a look at 7D now, and then next lesson we've also got some exam questions. Okay. So next lesson we can finish off 7D, questions 1 to 8. There's going to be some packs of exam questions with worked solutions that I've got, And you could also have a look at mixed exercise 7, and these questions here, 8, 9, 10, 11, 12, those have got moments in.